So I had two requests today for questions to answer in advance. So the first question was about how we do the 2D drawings of the 3D structures of cyclohexane. So there's three conformations we draw: the boat, skew boat, and the what's it called? Chair conformation. Now there's actually four. So the fourth one is the planar conformation. So I don't have my modeling kit here with me today, but we're going to try to do what we came with a whiteboard. There you are. So planar conformation, the way we draw that 2D is the way we actually just kind of draw cyclohexane in general. Is we have your typical 6 lines. So this is how we're always going to draw it when we do the 2D projections, simply because it's easier to work with this way, and it's easier to see Cis Trans when we do this. Now, for the boat and the skew boat, we traditionally don't have a special representation for those. So for the skew boat, or for the boat, what happens is that these two opposite carbons stand out, and so we end up getting our two sides, and we're going to have a wedge showing that these pop out of the board. Now, unfortunately, I don't have my modeling kit here with me today, but basically all a skew boat is that we take 4 carbons sitting in plane, and then the two opposite ends fold up, so it looks kind of like a C shape on the side, or kind of like a canoe. Now, for the skew boat, the way we would draw that is we would just kind of draw it angled off at a weird angle. So we kind of have this asymmetry. And what's happening with the skew boat is that if you build your 3D structure, you build it with a modeling kit, and you do the boat, there are 2 hydrogens on the tips of the boat that actually point at each other. What happens when you skew them is that you rotate them a little bit out of plane with each other. So the actual symmetry here, the halfway point, if you had a true boat, would have these 2 carbons sitting in line along the halfway point, and the 2 hydrogens would be really close to each other. By doing the skew boat, we get out of the steric issues of the hydrogens. Now, the bigger one is you get a type of eraser, is the chair conformation. So the chair conformation is actually what cyclohexane exists as naturally. And if you build cyclohexane and you set it up, basically what ends up happening with cyclohexane in the chair conformation is that all the groups are gauche to each other, and they're actually pretty close to the tetrahedral angle. So this is going to be the thermodynamically the most stable one. The way we draw that 2D is if you take your boat conformation and you turn it on its side and project a light through it, that's what it's going to look like. So the way I think about it when I see these drawings is that, so if we were to draw our cyclohexane, there's 2 arms to the chair, and then 1 carbon dips down, that's the feet. 1 carbon dips up, that's the that's the head of the chair. Sorry, I'm trying to think about how to draw this easiest for you. Sorry, I'm not used to drawing it at an angle. Give me just a minute. So when I see this drawing, to me, this is the foot of the chair. This is the head of the chair. And these two parallel lines here are the arms. Now, other books represent that this is the head of the chair, this is the foot of the chair, and these are the 2 arms. Honestly, it's not going to really change your answer. And if you see your answer varying slightly from others, it's probably just a rotation around the plane of the ring. So let me make sure I've answered that question. So this is how we convert the chair conformation to a 2D projection. Is we basically draw the chair and then draw it as if we have a shadow projection of it. So again, there's your 2 arms, there's the head and the foot. Now the other email question I got was about how you approach the problems that are on the discussion board. So this is actually kind of a nice, let's back up a minute. So when we have these cyclohexane rings versus a linear chain, what a linear chain can do that cyclohexane can't do is that we can get conformational rotation. So we can rotate along single bonds within a linear chain. It'll flop around. But when it comes to something like cyclohexane or cyclopentane or any of the cyclo compounds, we don't really get that much rotation. We can't do a 360-degree rotation. And because of that, if we were to crash, if we were to take our chair conformation and crash it down into, like, just take our hands and literally flatten it so that it was a plane, we would see that there are half the atoms that are attached to these carbons stick out of the board and half the atoms stick into the board. And so that's where this Cis Trans notation or EZ notation comes from, to designate which side of the plane they are on groups relative to each other. So a comment about Cis Trans. So you could only use Cis Trans if you have the same groups. And you only need to have two atoms that are the same. So if we have an R group, and let's say an R prime, even though the R and the R prime groups aren't the same, on the opposite side of the ring we have two hydrogens. So in order to use Cis Trans, whatever you're describing, among the two carbons, there have to be two groups that are the same or similar, or there has to be two groups that are present on each carbon. So if we use the Cis Trans for this one, we have an R and an R prime, so this could be a methyl and ethyl, it could be whatever. We would have to use the Cis Trans relative to the hydrogens. Now, if they're on the same side, we get the cis. And the way I remember this is that if you turn the ring on its side, you get a C shape. So this is your cis conformation. Trans would be if they're on the opposite side. So if we swap places here. So trans means the same thing as like transatlantic. Their prefix is the same thing. But they're trans, they're on opposite sides of the plane. The limitation with Cis Trans, though, is that it only applies if you have two groups that are the same. So let's say instead of an R and an R prime, we also had an R double prime, a third group. In this case, we couldn't use the Cis Trans, which is where we get to EZ. So EZ uses the CIP, the Kohn-Ingold priority rules. And what it does is that you assign a priority to each group on the two carbons. So we're going to split the bond in half. So in this case, we've got the R coming up, the R double prime coming down, the hydrogen coming up, and the R prime going down. Switch to see the live. So what we do for the EZ notation is on opposite sides we pick a 1 or a 2. Now we don't care about what else is in the ring. So the rest of the ring doesn't matter for this assignment. It only matters what's branching off the ring. So let's say R prime ranks higher in the CIP rules than the R. We have a 1 down and a 2 up. And over here, hydrogen's the lowest at second priority, R prime is the highest priority. Since they're on the same side, we would use Z. Now, it may not make sense why we say Z. Z is actually German, it's zusammen. So zusammen or zusammen means the same or together. So if they're on the same side, they're zusammen. If they were on opposite sides, so let's say this ends up being 2 and this ends up being 1. So the 1s are on opposite side, 2s are on opposite sides. We get GE, which is entgegen, or apart or opposite. So the EZ here will always work. So if you use EZ over Cis Trans, that's fine. You're still right. The Cis Trans is more of a colloquial one, and it's a lot easier because you don't assign priority rules. You just look at which groups are the same. But again, this only works if each carbon you're comparing has, each of them share a common group. So in this case, if they don't have a common group, you don't have like 2 hydrogens or 2 methyls or 2 ethyls, then you can't use Cis Trans. So let's talk about how you approach this problem in the discussion board. So in this discussion board, I give you 4 compounds, and all of these you can use either EZ or Cis Trans. It doesn't really matter, because for every single one, we have this, each carbon contains a hydrogen. So our Cis Trans here is going to refer to the hydrogens, assuming that these groups coming off aren't the same. So if we look at compound 1, we have a methyl group going down and an ethyl group going back. Or we can think about it that this methyl group has a hydrogen going back and this ethyl group has a hydrogen coming forward. Well, since the hydrogens are on opposite sides of the ring, this would be a trans compound. So to name it, do what you've done before with alkanes. Name the parent chain. In this case, it's cyclohexane. And actually, I'll bring it up. So to approach these types of problems, you're still going to use the same approach you use for naming linear alkanes. This EZ comes at the front. So for all of these, our parent chain here is cyclo. Oh, you can't even read that. Or if you can, your eyes are better than mine. Bring up a Word document. Yeah, I know. So all these have the parent cyclohexane chain. Now we have a methyl group and an ethyl group. So it's an ethyl-methyl cyclohexane. We need to minimize the numbering, so the ethyl is going to come first, the methyl group is going to come second. This is what you would name it if you didn't have those wedges and dashes on it. Now, to do the cis trans, well, we're going to compare the hydrogens. Since the hydrogens are on opposite side, this would be trans 1-ethyl 2-methyl cyclohexane. If you want to do the EZ, well, the ethyl group is a CH2, the methyl group is a CH3, so by the Cunningham priority rules, well, I mean, they all outweigh hydrogen, so carbons are on opposite side, they're higher, they're opposite, so in this case you have the int gain, the E, 1-ethyl 2-methyl cyclohexane. If you want to switch over to compound 2, same line of reasoning. It's still a 1-ethyl, now it's a 3-methyl because we've moved it 1 carbon away. They're on opposite sides, so it's still trans, and they're still on opposite sides, so it's still E. And 3 and 4 are going to take the same approach. Write out the name of the parent chain, write out the branches, write out the positions of the branches, and then the cis trans EZ is the last step, because it's just kind of one last identifier. It actually starts narrowing down the stereochemistry. So if you can name a linear branched alkene, you can definitely do the cis trans EZ notation. So these were all the pre-assigned questions I got asked. Are there any other questions from the people watching the video or the one person watching concurrently? Now the cis trans EZ is going to have a lot of implications about whether they're both axial, if they're both equatorial. For stability, larger groups like ethyl, propyl, butyl, big chains prefer to be equatorial. Short, small ones like hydrogen and methyl groups prefer to be axial. If we have two alkane branches, if they can both be equatorial, we'd prefer them to be equatorial because hydrogen would always be best in the axial positions. But if we have to choose one, meaning that one's going to be axial, one's going to be equatorial, then in that case, we're going to do whichever one puts the larger group in the equatorial position. But again, you can't really look at this T, because you can get interconversion of axial and equatorial positions, this cis trans doesn't make any implication about if they're axial or equatorial. As drawn, there are no axial or equatorial bonds when cyclohexanes are represented as this flat ring. But we can assign one as an axial, and then their relative positions along the ring will dictate whether or not the other one is coaxial or if it's equatorial. So again, are there any other questions? All right. If there are any other questions, I'm just going to sit here and strum the guitar. Feel free to answer any questions you have. I'm just here in case you need me. Ooh, out of practice. All right, question 25 on the homework. And thank you for the compliment on the guitar. I finally upgraded from the one I had in college for years and years and years, so it actually sounds good. By the way, if Sam Ash ever recommends you buy a Carlos Rebelli guitar, don't buy it. Let's see here. Assignments. Homework assignments. Test 2. Desperately need to change my fingernails. So that's going to be my excuse for why I'm struggling going between chords right now. And question 25. So switch to the desktop. Give the IUPAC name for the following compound below. Be sure to enable all the parts. So we've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So the longest one here is going to be octane for the parent. And if we do octane, we have an ethyl and a trimethyl. So your ethyl is going to come first, and then you're going to have trimethyl octane. So you got those filled in. Now we want to minimize the position on the ethyl group, so it's 1, 2, 3, 4. So if we go from the right side, it's 4 carbons over. We'll go from the left, 1, 2, 3, 4, 5. For the methyl, it should be 3, 5, 7. Now let's see what they're saying. I disagree. So let's see if they're doing that on instance 5. 2, 4, 6. So you see where it's actually contradicting itself in this answer, so that the first substituents get the lowest number. But here's the thing. Let's see if it'll let me clear the attempt. So here's the problem if we do exactly what the instructions are telling you to do. Your trimethyl octane. If we want to minimize the numbering, ethyl definitely comes in the 4th position. And then everything else is set. So 3, 5, 7. Now, if we number it the other way and we do the 5, I'm going to keep the numbers off to the side for my own reference. We have 4, 3, 5, 7 versus 5, 2, 4, 6, 17. There are some texts that argue that the IUPAC here should minimize the sum. So if I do the 4, 3, 5, 7, I add that up, I'll get 19. And then I go to the 5, 2, 4, 6, and I get 17. So here's the problem with this argument. Every book I have read, Francis and Carey, multiple editions of it, have all said that the goal here, and you saw it with the answer, is to minimize the position of the first substituent. You will see this pop up on Reddit as well as other sources saying, no, the goal here is to minimize the sum. So really it should be 5, 2, 4, 6, because 5, 2, 4, 6, if you add that up, you get 17 versus 19. The way I teach it and the way I'm going to teach it, because this is from what I've been able to see about IUPAC and basically even the Chemistry Libre text saying this, it should be minimizing the first position. So what I'm going to do is I'm going to remove this question. But yeah, if you catch that in the directions, remember the number of the long chains, so the first substituent gets the lowest number. The first substituent here is ethyl. Now they may be referring to that if you go to the either end, well, now you need to minimize the methyl. Not what I was taught. So hopefully that answers your question, Lauren. In fact, let me update that right now. Right. Any other questions out there? Yeah, it's kind of weird, but honestly, it doesn't come up that much, so we'll see. I'll see how I try to readjust it for future semesters. numbering on the carbons in the ring versus numbering the carbons in the chair conformation. So they're numbered. So when it comes to numbering the carbons, we're going to number them the same way we do for regardless of the conformation. So when we name it like it's a planar ring. That makes it easier to find the cis trans. So in the discussion board, your ethyl group comes first, so you're going to number that one first, just because it comes earlier alphabetically. And, excuse me. So I guess the way to put it is that when it comes to numbering the carbons, we don't care if it's in the boat, the chair, the skew boat, things like that. We're going to name it like it's just drawn as that flat cyclohexane ring or cyclopentane or any of those. As far as the cis trans go, the cis trans refers to two of the same groups. So with all of these, we have an ethyl and a methyl group attached to a carbon, but there's two bonds. There's a hydrogen that's there that isn't drawn, and it's never drawn unless there's a reason to think there's a reaction going on with it. So for the cis trans version of those answers, those cis trans versions are referring to the hydrogens, where the hydrogens are both wedged or both dashed for cis, or if they're one's wedged, one's dashed for the trans. EZ is going to work in a similar fashion. We're going to compare to see if the higher priority groups are on the same side or opposite sides. So if the higher priority groups are both wedged or both dashed, we would say that this is Z, zusammen, which means together. And if one high priority group is wedged and the other one's dashed, then we would say they're entgehen, E, meaning opposite or opposed. Yeah, you're very welcome. I hope you do well on the quiz. Like, I always worry like what I'm saying is wrong. So, like, that full disclaimer that, yeah, well, sometimes instructors make mistakes, but good luck on your medicinal chemistry quiz. Do you have any questions for me? Yes. It doesn't matter whether you count clockwise or counterclockwise. The idea with the IUPAC naming being that you'll get the same answer regardless. The point is getting the making sure that their relative orientations in space are correct. So by bulky groups, we're referring to things that are basically branches on a chain that contain a lot of carbons. So hydrogen is the smallest atom attached to carbon in any of these organic compounds. So let's say we draw cis, 1 ethyl, 2 methyl. Now in this case we've got a CH3 group and we have a CH2, CH3. So if we just look at it in terms of atomic weights, this weighs 17. Let's see here. Yeah, not 17, 15. This weighs 15, and let's see, we got 14 plus 15 gives us 29. So while they're not shown here, this has hydrogen sticking off of it, and this has hydrogen sticking off of it. There's also hydrogens coming off the opposite sides. So because they are cis, 1,2 cis compounds, one of these is going to be axial, the other one is going to be equatorial. So the thing about equatorial is that if we were to turn this ring on its side and actually draw, if I actually had my modeling kit with me, we could show it, that on the edge of the ring, we have axial atoms standing up and down, and then we kind of have these equatorial atoms hanging off to the side. So our axial groups are actually held in close proximity to each other, whereas our equatorial bonds, if we were to look down the ring, kind of flare off to the edges. So axial positions are more sterically hindered than equatorial positions. So in our previous example of the ethyl-methyl, the ethyl group is bigger because it has more atoms around it, or it has more atoms associated with it. So we would rather stick that in the equatorial position where it has a lot more room. So our ethyl group would stick out here, and our methyl group would hang up in the axial position. Now, that doesn't mean axial doesn't have steric hindrance. I mean, there's still like hydrogens coming off that methyl group. But those hydrogens don't take up nearly as much space as the rest of the ethyl chain. Yeah, bulky groups are just anything that has a lot of atoms associated with. So again, hydrogen is going to be your smallest group. Like it's a single hydrogen atom. It's roughly it's roughly 10 nanometers wide. 10 nanometers? Yeah, 10 nanometers wide. But something like carbon's much bigger than hydrogen, and that carbon has other hydrogens associated with it. It's kind of a detail that's lost on these line bond drawings because we intentionally leave off the hydrogens, but they are there and they're sticking off and they're pushing against other groups. Now, ideally, we could put every group equatorial. So if we had something like a 1,3 cis, in this case, they're both axial or both equatorial. So even though this is just shown as a planar drawing, if we were to do the chair conformation, we'd actually put both of them in equatorial positions. So the more stable conformation is when where both the methyl and the ethyl group are equatorial. Now, they can both be axial, and they will exist in the axial position to an extent, but a majority of the time they're going to spend energy in the lower co-equatorial positions. Other questions? The best advice with organic chemistry is really the foundation on which it's built. So the way I teach organic is we start with characterization, and now we're moving into alkanes. So one thing you need to get is modeling kit if you don't have it. And there are varying degrees of good modeling kits, so I'll send you a link to the one that I send my students to. But a modeling kit is an essential thing because right now I can see it, but I've been doing it for a while. But even now, even with me, it's a bit of a challenge. So I'll post the link in the comments section. But I would recommend getting a good modeling kit and building a lot of these things and getting used to working with them. When it comes to naming, there's a reason we teach the alkanes first, because pretty much everything is built off of if you can name any type of alkane, so if you can name a cyclic alkane and you can name a branched alkane, everything else kind of follows that similar pattern. There are differences on the priority. So alkyl halides usually follow alkanes in terms of instructions, but alkanes and alkyl halides, basically the halogens follow the same priority as the hydrogens and carbons. So they're named the exact same way. You just treat the halogen as a branch. Alcohols are actually easier to name than alkanes because when it comes to alcohols, we want the alcohol to come, we want its position to come first. So you do, the way I teach it is organic compounds are named right to left. So, few things. We have the parent. So your parent here is going to have a prefix. And this prefix is going to designate the number of carbons and if it's a cyclo. Now, there's a little suffix at the end, and this is the functional group. So if you have ANE, it's an alkane. Now, introduce this slowly. We start with alkanes because they're the easiest name, but the group that gets the suffix at the end is the most reactive group. So that's where that comes from. Alcohols are more reactive than alkanes, so when we go to alcohols, this ends up being an OL ending. When we go to ketones and aldehydes, we start changing the prefix to designate that they're in there, and the most important group is listed in there. Now, because we have an A and E, it means that the alkane groups are the most important group, so basically our priority is going to minimizing their numbers. If we go to an OL ending, an alcohol, then the number associated with the alcohol takes the highest priority. Everything beyond this are branches. So before you even try to number where they are, just write out the branches. And again, the branches go in alphabetical order. They ignore the cyclo. So if you have a cyclohexane, cyclopentane, that doesn't go towards the alphabetical order. And on top of that, we ignore like the di, tri, and all that. So if you have more than one methyl group, we have to specify it. Dimethyl, trimethyl, tetramethyl, same thing with all the other groups. So organize the branches in alphabetical order, and then we put in the numbers. So we need to specify where they are. And the goal here is we want to minimize the numbering. And the reason being is that when we go backwards, we want to make it easier on ourselves. So when you go backwards, you write out how many carbons are in the parent chain, so you just draw it out. Put the functional group at the correct space if there's need to, which sometimes there is for alcohols. And then you just arbitrarily start numbering your carbons. So usually people do it left to right, 1, 2, 3, 4. And you can figure out based on the numbers where you're putting these branches and what those branches are. There is additional information out here, and this is the stereochemistry. So we're going to write SC for stereochemistry. So this is where your EZ, Cis Trans, RS if you're doing chirality, all of that sticks to the end. If you try to go left to right when you do the naming, you're going to struggle because you're putting too much, you're trying to do all the hard work up front. The way the naming works is most important functional group first, length of the parent chain, the branches, the numbers, and then finally at that point you can start naming any type of stereochemistries that happen. As far as energy goes, it's pretty much all sterics. We're trying to get things as far apart as possible. So when it comes to cyclohexane, if we can get everything into the equatorial position, it will be more stable. Ideally, chains are staggered because it puts all the big groups opposite each other along a double bond. And yeah, that's the bulk of it for Organic 1. The rest are reactions and how to study reactions. My recommendation for studying reactions, write the reagent, write what it reacts with, what functional group it reacts with, and what functional group it creates. So something like potassium permanganate, KMO4, reacts with an alkene, a double bond, to form a diol or a ketone. And so you have what it reacts with, what it forms, and any stereochemistry. So if it's stereospecific, meaning that it converts an R to an S, or we get an inversion of symmetry, that's important to note. If it doesn't have any stereo effects, that's important to note. If it only has stereo effects under certain conditions, that's important to know. So something like potassium cyanide, KCN. the cyanide will displace a halogen. Now, in a polar protic solvent like water, it will create a racemic mixture, or mixtures of R and S chiralities. Under something like dimethyl sulfoxide, DMSO, which has its aprotic and low polarity, it actually does an SN2 mechanism, and that gives you chirality inversion. So write those out. And honestly, the best way to learn reactions from my experience was to do synthesis problems, because it forces you to apply it. So you start with one compound and you want to make another, and you go through your flashcards of the different reagents, what they do, and you try to find the ones that kind of like get you to where you want to go. But later videos I'll be talking about, when my students finally get to synthesis, we'll talk about how to approach a synthetic scheme. And there's forward and reverse engineering that gets associated with it. There's a bit of an art to it, but honestly, it's one of those things, I think if you do it about 5 or 6 times, you start picking up on the pattern, and then harder problems are just more steps. Yeah, I know that was a long answer to your question, but yeah, I think for me, the biggest thing that makes organic chemistry easier is just having a good foundation. If you understand how to name alkanes, everything above that is just little details, like little nuances. If you know how, like, if you start breaking reactions down, you can break them into simple parts. For me personally, naming is the hardest part because there are so many details. Now, again, this is from an instructor who's teaching organic too, and you can get some like nightmare compounds. There's like 12 functional groups in it. So maybe that's why I'm biased towards the naming being the hardest part. But as far as reactions go, there's also the hard reality that you can make a problem arbitrarily hard. Good for you. The truth is, we like to keep synthetic schemes simple, because the more steps you have, the worse your yields are going to be. I have a student right now, her dad's a practicing organic chemist, and I talk about in my notes how it's weird, like some instructors really think you should be able to derive the structure from like the NMR and things like that. And it's weird because if you talk to anyone that did it for a living, they're like, why on earth would you do that? You would go to a database and compare it to a database. Now, you need to understand qualitatively why it works the way it is. Like, you need to understand where splitting patterns come from, be able to predict basic splitting patterns. But nobody just like blindly walks into a lab and runs an NMR and says, gee, I wonder what I got. Usually what happens is they're running a reaction and they have a pretty good guess as to what they probably have. And if you know what you probably have, you can make some pretty good guesses as to what you should be seeing with the 3 basic analytical techniques, NMR, IR, and mass spec. And if you don't get that, you know you didn't make what you thought you made. But because you know the reaction conditions, you also know what you probably could have made if you didn't make what you thought you made. And you can compare them to those. But almost in practice, nobody really does this like reverse engineer it. You're really kind of dealing with troubleshooting problems at that point. But yeah, I don't really teach NMR with the standpoint of you need to be able to identify it with no outside information. No, you're always given outside information. Very rarely do you not have that. And again, your point is to figure out what you made, and you should have a good guess as to what you were trying to make. Other questions? All right, give it about another minute. If there are any questions, we'll just sign off a little bit early today. Yeah, you too, Lauren. Thanks for showing up. All right, if there aren't any other questions, thanks for y'all showing up today. And again, live streams are Monday and Wednesday, 10 to 11, Thursday, 12 to 1, and then Friday from 2:30 to 3:30. Orgo 1, Orgo 2, you both have exams starting next Monday at midnight, or first thing in the morning, midnight, and they'll carry through. You have until Sunday, following Sunday at midnight to finish the exam, and the homeworks are due Friday night. All right, I will see the rest of y'all hopefully this week.